All right, welcome back to Math 3322. Today we're going to talk about Chapter 8, Section 1. Chapter 8 is all about algebraic thinking, and Section 8.1 is here to help you start thinking about working with variables. So you will be able to use variables to translate word phrases into algebraic expressions, solve equations and word problems, and you will also learn about arithmetic and geometric sequences. All right, so variables are generalizations used for generalizations of patterns. And if we were to use actual values instead of variables, then the instructions would only apply to a limited set of situations. So a variable can be an element of a set or a set itself. So for example, in the intersection of two sets, A intersect B is all of the elements X, where X is in A and X is in B. And X is any element that belongs to both sets. So those sets could be anything. It could be colors, it could be numbers, they could be more sets. So we're going to use usually like X and N a lot. Typically, we could choose a number or a letter, excuse me, that makes sense, that reminds us of what it stands for. So if we have a situation where the cost of renting a car for any number of days is $40 a day, then we could say N for the number of days, D for days would make sense. But if we want to write this in an algebraic expression, we could do 40 N dollars is the total amount of your car rental, where N is the number of days. Oh, and then if we want to know the distance of a car traveled at a constant speed of 65 miles per hour for any number of hours, then we can say N is any number of hours, H is the number of hours, but we're going to multiply 65 times H hours to figure out how many miles, because we're going to drive 65 miles per every hour. Okay, so here's an example. If we have a store that's selling twice as many 8 GB flash drives as 64 GB flash drives, and 25 fewer 256 GB flash drives than 8 GB flash drives, if the store sold D 64 GB flash drives, how many 256 drives and 8 GB drives did it sell? So we know that they sold twice as many 8 GB flash drives as 64 GB flash drives. So the 8 GB flash drives are going to be 2 times the number of 64 GB flash drives, so 2 times D, or 2D. We know that they sold 25 fewer 256 GB drives than 8 GB drives. So I need to take that number of 8 GB drives and subtract 25 from it. So 256 gigabytes. So the number of 8 GB drives is 2D minus 25 to get the 256. So if I knew that they sold D equaled 164 flash drives at 64 gigabytes, then I could find out there were 208 gigabytes and 175, 256 gigabytes. All right, so here's another example. If we have Mateo is going on a diet and he thinks that he needs to eat 1,200 calories a day, he's going to eat some French fries and a hamburger. French fries have about 3 calories each, and a hamburger is about 250 calories. If he ate F French fries and 1 hamburger, how many more calories can he consume that day? So his total needs to be 1,200, and the number of French fries is F. So the number of total calories from French fries is going to be 3F plus the 250 calories from the hamburger. And to figure out how much he can have the rest of the day, we can subtract this number from 1,200. All right, so this is going to write out that idea for us. So if 1 French fry, the number of French fries is 3F calories. And so total is 250 plus 3F, and then we subtract that from 1200, and then you can simplify that expression, not forgetting to subtract both 250 and 3F. So when you end up, you'll get 950 minus 3F. All right, so in this example, a teacher instructs a student. They say, take any number and add 15 to it. Now multiply that sum by 4. Next, subtract 8 and divide the difference by 4. Now subtract 12 from the quotient and tell me the answer. I will tell you the number, the original number. So if we want to understand what this teacher's telling the student to do, they say take any number and add 15 to it. So let's let n be any number. So they first say add 15 to that number. Multiply that sum by 4. So I need to take the whole sum and multiply by 4. Next, subtract 8 and divide the difference by 4. So I'm going to take this whole thing, subtract 8, and then divide that entire difference by 4. So I'm going to use a fraction notation, divide by 4. And then subtract 12 from the quotient. So I need to subtract 12 from that entire division. And the teacher claims they can tell you what number you started with. So let's see what is going on here. So if we want to go ahead and simplify this expression, then we can distribute our 4 to this addition. So we're going to have 4n plus 15 times 4 is 60, minus 8 over 4. And this is all minus 12. Then we have 4n plus 60 minus 8 is 52, divided by 4 minus 12. Now 4n is divisible by 4, so 4n divided by 4 is 4, and 52 divided by 4 is, 52 is divisible by 4, and it will be 13. So I can divide both of those numbers by 4, and I get n plus 13 minus 12. And so that means the number is just n plus 1. So if you tell the teacher the result from all of this work, it's actually just the same as n plus 1. So if you come back and say, my answer to all of those calculations was 150, then the teacher knows that your original number was 149. All right, so let's walk through how the teacher might have come up with this idea. All right, it's not letting me erase that. Let's share again. All right, so what the teacher did, or this is just a discussion of what I just showed you. So add 15, multiply by 4, subtract 8, divide by 4, subtract 12, and that's what we ended up with. So how did the teacher figure this out? So the teacher is told the answer obtained, and then she produces the original number. We can use the work backward strategy to determine what happened. So if we determine that the final result is R, then that last step was to subtract 12. So we can add 12 to reverse that operation. Then the step before that was to divide by 4. So we can reverse that by multiplying by 4, R plus 12 times 4. And then the step before that was to subtract 8. To reverse that, we add 8. The step before that was to multiply by 4. So we divide by 4. So we end up with R plus 14. Before that, we were to add 15. So now we're subtracting 15. So we get R minus 1. Thus, the original number is one less than the result of, or the result is one more than the original number. So we can either work forwards as I did, or work backwards as the slides have illustrated. So then we are going to think about sequences and how we can represent them algebraically. So this figure shows a sequence of figures containing small square tiles. Some of the tiles are shaded. Notice that the first figure has one tile shaded. The second figure has two squared tiles shaded. The third has three squares tiles shaded. And so we could represent the sequence entry, if we want to call the entries of the sequence A sub n. So this would be A1, this would be A2, this could be A3. AN is just given by n squared. So a couple other types of sequences that we're going to learn about are arithmetic and geometric sequences. So an arithmetic sequence is a sequence where the difference between the consecutive terms is a constant. So we're adding or subtracting the same amount to get from one term to the next. But a geometric sequence is where we have the ratio being multiplied, a ratio being multiplied to the previous term. So the ratio is constant between terms and we're multiplying some same number every time. Now, we can think about this recursively. So to get from one value to the next, we just add this difference d. So if we want an, we take the one before it, we add the same difference as we've noticed in our patterns. And then same thing for geometric. We can figure out the nth sequence of the term by just multiplying that ratio to the previous term. But what's going to be more useful for us is if we can find any term of the sequence using a formula. And so the way we can do this for an arithmetic sequence is the nth term is going to be given to us by taking that first term and then adding d to it n minus 1 times, because we have the first term. So to get to the second term, we're going to add d 1 time. So 2 minus 1 is 1 would be what we have here. So we need to add it one fewer time than the number of term we're looking for because we started with the first term already. And then for geometric sequence, it's very similar, except for we're going to multiply the first original term by r n minus 1 times. So instead of adding d n minus 1 times, we're multiplying by r n minus 1 times. So let's just look at one example from each of these. These are sample homework problems. So if we were given, say, this sequence in the middle, let's say we have 2/3, 1, 4/3. We need to find the 100th term and the nth term. Now, the easiest way for us to do that is going to be to use that explicit formula. So in this case, A1, the original term is 2/3. And the difference between each of these terms, we're actually adding 1/3 every time. So a to the n is going to be given by 2/3 plus n minus 1 times 1/3. So the 100th term, so a 100, will be 2/3 plus 99 times 1/3. And this is 2/3 plus 99/3, which is 101/3. And then the nth term is just this here, which you could simplify. And I think my math lab homework may want you to simplify. If we look at geometric sequences instead, so let's take a look at part C here. We need to find the 9th term and the nth term in this situation. Now here, our original term is -1/3. And so we have to figure out what's happening between each of these terms. How do we get from 1/3 to 4/9? So to get to 4/9, and we're multiplying -1/3 times something. When we multiply fractions, we multiply the numerators and multiply the denominators. So if I want 4/9, I know I'm going to have to multiply by something negative because I'm going to have a negative times negative, giving us a positive 4/9. And I need a 4 in the numerator, 4 times 1, and I need a 3 in the denominator. So I get 3 times 3 is 9, -1 times -4 is 4. So our ratio here is -4/3. So a n term is going to be -1/3 times -4/3 to the nth minus 1 power. So a 9 is -1/3 times -4/3 to the 8th power. And you can simplify that based on our previous lesson. Okay, and then a final type of sequence that we have is the Fibonacci sequence. So Fibonacci sequence is not arithmetic and it's not geometric. And the way we get the typical Fibonacci sequence is we start with the numbers 0 and 1, and the next number is found by adding the two previous numbers. So if we start with 0 and 1, then we do 0 plus 1 is 1, 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, 5 plus 8 is 13, etc. And so we can write this recursively using the rule xn, the nth term, is the sum of the n minus 1 term plus the n minus 2 term. So taking those two previous terms and adding them together. So we can have a Fibonacci type sequence with any two original numbers. So you can have 0 and 5. You could have 5 and 7, and then you're going to get a different Fibonacci sequence. But you just start with two numbers and you get the next term by adding them together. You get the term after that by adding the previous two together, etc. So if I wanted to do 0 and 5, for example, then the next term would be 0 plus 5, 10. Then 5 plus 10 is 15. 10 plus 15 is 25. 15 plus 25 is 40, etc. And I do 25 plus 40 and keep going. Okay, next example. So if we're not given the full arithmetic sequence, but instead we're given just a number, a couple of the terms, then we can figure out the pattern. So in this case, we know that the second term is 11 and the fifth term is 23. So if the first term is 11, or sorry, the second term is 11, then I know that we got it by taking A plus D. And so I also know from 23 that I have A plus 5 minus 1D is how we got 23. And we can simplify that to A plus 4D. Now, I can solve these two equations and find what A1 and D are. So I know if I take A1 plus 4D, I know A1 plus D is 11, but I can also split this by taking one of the D's and three of the D's apart. So I can simplify, this is A5, right? That's the 23. And so I know A1 plus D is 11. So 11 plus 3D is 23. And I can simplify subtracting 11 from both sides, dividing both sides by 3, and getting D equals 4. And so to find what A1 was, I know that A1 plus 4 is 11. So that tells me that A1 has to be 7. And then to find the 100th term, we can use our arithmetic formula, we know that A1 is 7, D is 4. So we put 100 in for N and we will get 403. Okay, now we have a geometric sequence and we want to find its nth term. We can find the multiple. So in the previous example I showed you, we had fractions and it was maybe easier to think about what am I going to multiply to get from one to the next. But we can also just divide the two consecutive terms. So the ratio of the sequence can be found by dividing two consecutive terms. So if we take 3 and divide it by 2, that's our ratio, 3 over 2, because 2 times 3 over 2 will give us 3. So the formula for the nth term, we have that original 2 times the ratio to the n minus 1 power. And if we don't have the whole sequence, we just have information. So we know the first term is 3 and the ratio is square root 2. Then we know that A1 is 3, R is square root 2. So we should get the 10th term is 3 times the square root of 2 to the 10 minus 1 power, and that's 9. And we can simplify that. This is okay, so there's actually an error here. This should be a 3. I'll fix that and repost these slides. But so we have the square root of 2 to the 9th power, which we can always write square roots as a power of 1/2. We can simplify this by splitting up 8 over 2 and 1 over 2 powers. And then we have 2 to the 4th power, which we'll get from this one. 2 to the 4th power is 16. 16 times 3 is 48, times the square root of 2, which we get from that. So that's just using what we did in the last lesson to simplify our radicals and roots. So that is all I'm going to do for this video, but I hope it helps, and let me know if you have any questions.